All right, here we go with the third part of lesson 1.4. So in this one, we are looking at something called the intermediate value theorem. A little more to say on this on page 94 of the chapter 1 calculus book, so you can always take a look at that. We're going to look at one figure in there together, just so I can give you a little visual as to help explain the intermediate value theorem. So let me take you to this guy for a minute. So here's basically what it says. So here is a ongoing function, and here is an interval from a to b, right? So a and b are x's, which means f of a would be a y coordinate, and f of b would also be a y coordinate. So if c represents any x coordinate in the interval from a to b, and k represents a y coordinate between f of a and f of b. So since this is a continuous function from a to b, there must be at least one value for c that pairs up with that k as a y coordinate. So that's pretty much all it says. If it's not a continuous function like this, then there does not have to be an x coordinate, a c value, that pairs up with your k value. Right? So f of c does not have to equal k if it's a discontinuous graph. Right? So only if it's a continuous from a to b do you get this statement right here. So that's our intermediate value theorem. So let's take a look at a couple things here. Try to get all that relevant stuff on the screen for you. Okay, so if we had this function right here, does f of x, does this function have a 0 in the interval from 0 to 1? So does it have a 0? So here's our interval from 0 to 1. So first thing we got to figure out is it continuous, right? And we know x to the third would look something like this. So we know it's continuous within that given domain. So we are looking at what would be f of 0 and what would be f of 1. So we're looking at, these are our x's, and I'm plugging in 0 to get a y coordinate for him. That's this guy. Plugging in 1 to get a y coordinate for him, and that would be this guy. So these are the x's from 0 to 1. They have y values from -1 to 2. So here's kind of a diagram for that. So I'm looking at my x's from 0 to 1. The y coordinates went from -1 to 2. And again, it's continuous. That's what we first had to figure out, was kind of the main thing on this. So we first decided, yes, that is a continuous function, which means it has to be continuous from 0 to 1, which is why that's one connected curve right there. So does there have to be a 0 within that interval? And when they say a 0, what they're referring to is an x-intercept, right, is what they're referring to. In other words, at an x-intercept, we know you'd have a y coordinate of 0. So that's really what they're asking, is within this interval where x is 0 and y is 1, within that interval, would I get a y coordinate of 0? So if you look at the graph, that's really easy to see that yes, that would have to exist because it's a continuous function all the way from here to here. So it must pass over the x-axis, which means there would have to be a 0 or an x-intercept within that interval. So, and this is kind of the conclusion that you're seeing on this. So since it's continuous from 0 to 1, the range is the -1 to 2. If this is my range, and I go from -1 to 2, somewhere between this and this, I have to pass over 0 along the way, right? So this statement must be true within this domain, is what they're asking us. So let me give you just another example along those lines. So here's kind of the same process that we're seeing on this one. All right, so what we're looking at on this one, I'm giving you a tangent function, and we are given the domain of 1 to 4. All right, and so first things first, is it continuous from 1 to 4? So the first thing I did on this one was I just did a sketch of the graph. So remember, for a tangent function, we do pi over b, and that gives us one period of the function. And for a tangent function, these guys are centered at 0. So if one full period is 10, then I would go 5 to the left and 5 to the right to get my two asymptotes. right? And I know that between the asymptotes, it's always a tangent function is always continuous between the asymptotes, right, on something like that. So one limit that we're going to see on this, or limitation of the graph, is it continuous from here to here? It would not be, because of this piece, this vertical shift. I can't have 0 for x. So it would not be continuous where x is 0. However, that's outside of this domain, right? So it's still continuous from 1 to 4. So if, say, x is 1 is about here, and x is 4 would put you somewhere over here. So it is continuous from 1 to 4 within that little portion of the graph. And so yes, it's continuous. So that's kind of the first thing you got to look for. Does it have a 0 within this domain? So that's like the question that we're being asked. Well, if it's continuous from 1 to 4, let's take a look at what the y-coordinates would be at 1 and at 4. So that's what I was doing right here. So if you plug in a 1, you get something like this. Plug in a 4, you get something like this. Well, you'll notice on this that that this graph would go at 1, it's at negative 4.7. At 4, it's all the way up to 1.8. So it went from a negative to a positive within this portion of the graph. Now, when I did this graph, I was just checking for continuity within this domain. So I didn't even include the vertical shift on this. So it's not really, this exact graph wouldn't match this full expression if you were to graph it. So I get that, but that's really not what I was looking for on this. So for this guy, just from 1 to 4, you can see that our y-coordinates go from a negative to a positive. So in order to do that, it would of course have to pass over 0 for that to happen. So because it's continuous from 1 to 4, and my range goes from here to here, yes, there would have to be a 0 that exists from 1 to 4, somewhere within that. So that's our intermediate value theorem. Let me show you this one, something I wanted to show you on the calculator here. So we're going to find the zeros of, so I threw in something a little more complicated so we can get the zeros on this. So I'm going to be in radian mode here. When you graph something like this, you can have many, many zeros along the way. But that's why we're given a limited domain so that I find a certain 0 within the function. And so one way to simply do that, so I'm just going to graph the whole thing. So 2 cosine x minus 3x. And I'm only going to graph, so I'm going to go to my window. I'm only going to go from 0 to 1. And so that way I can only possibly get the one that they are asking me for. All right, so it's almost like we're zooming in on this one particular area of the graph. So that is the full graph, but it's only seeing the domain from 0 to 1. Super obvious that I have a x-intercept or a 0 right there in the middle. So if I want to get that, all I have to do is go under calc. So I'm going to hit second, go under calc, and we're going to find the 0, option 2. It's going to ask you a couple questions. You do need to answer these correctly. So for the left boundary, you just have to be anywhere to the left of your intercept and hit enter. And it's going to throw up a little boundary line. When it says right boundary, now I have to be anywhere to the right of my intercept and hit enter. And so what we're doing is we're giving the calculator a boundary for where the 0 is located. So now when it says guess, just hit enter. And it's going to give us the x-intercept for that portion of the graph. All right, let me flip over here to the last part. So just to verify the intermediate value theorem, and then we are solving for C. So again, the first part of this is just determining, is this a continuous function from 0 to 3? Right, we know it would be continuous. This is a cubic function. Those guys are continuous from negative infinity to positive infinity, so it has to be continuous from 0 to 3. So that's kind of the first step on this. The second step is, what are the y-coordinates that go with 0 and 3? So I'm going to plug in the 0 to get this y-coordinate, plug in 3 to get this y-coordinate. And so what we're trying to figure out is, is there a value for 4 within that range, right? So as I look at these, since my range goes from -2 to 19, and because it's continuous from 0 to 3, it must have a point where y is 4. All right, so yes, this does exist. And so now we're just solving here. So here's what you're seeing on this one. Really all we're doing is we are taking this function that you see right here. We're plugging in this information. So I'm putting in a c for x, and I'm setting the whole thing equal to 4. And so that's where this equation is coming from. If we subtract our 4 over to the other side, so that the whole thing can equal 0, we get this guy to solve. So solving this would actually take you back to your Algebra 2 days, where you solved polynomials. So I got to give you a quick refresher course on what that looked like. This has been a long time. You would have done this in your first semester of Algebra 2. The way that you solve this, this goes back to something called synthetic division. We're not going to go through that whole process. I just wanted to give you a reminder of how all this started. Possible solutions to this are always found by taking factors of this and dividing it by factors of your leading coefficient. So I'm taking every factor of 6, dividing it by every factor of 1. And so these are the potential zeros that I could have. What we are looking at is we saw that the domain was only from 0 to 3. Right? So as far as these are possible x's here that would create the zeros. So as I look at these possible x's, well, within this domain, I can only look at +1 and +2 as options. So those are the only two that I would have to test. So as I look at this, if I were to test 1, so if I plug in a 1 for c, it definitely does not equal 0. If I plug in a 2 for c, I do get 0 as my result. All right, so if I plug in that 2, I'm confirming that c equals 2, and so I have the point on that function of 2, 0 is what that would give us. So that is the end for part 3, and until next time.